Okay, so this video is going to talk about how reheat coils work. And so we've already talked a little bit in a previous video on how we use the heating coil and cooling coil at the central plant, or the central air handler, to create the desired supply or temperature. But now we need to talk about how the reheat coils work to add heat for the zone level. So in this example, we're going to have 55 degrees supply air temperature, and we're going to have an average of 95 degrees going out to the spaces. So just because we've got an average of 95 doesn't mean we've got 95 coming out of all the boxes. What we're trying to say is that on average we've got 95 going out. So if this is working properly, we should have one of these boxes supplying 55 or 56 degrees, and that means that this little reheat coil is barely doing any work. And then maybe we've got 105 going out of this box, and 95 going out of this box, and 85 going out of this box. And so on average, we've got 95 degrees going out to all the spaces. When a system is tuned properly, the supply air temperature should be just lower or close to the zone calling for the most heating, or sorry, for the most cooling. And so this 55 would be best if it matched like this zone here. And so in this case, we have a properly running system. But without the reheat coils, we'd be freezing out all these other zones that need heat. And so what we have to do here is we have to look at the equation of 1.08 times CFM times delta T again. We're going to say that this air handler right here is supplying 10,000 CFM. So our equation is 1.08 times 10,000 times the delta T, which is the delta T between 55 and 95, so 40 degrees. So first we want to figure that out. So that equals 432,000 BTUs per hour. And then that we're going to need to convert into a unit of power. So we can either multiply time first, or we can multiply and figure out power first. But let's figure out how much electric resistance kW is going through any given hour. And so what we have to do is we have to divide this number, and we have to figure out what the kW equivalent of 432,000 BTUH per hour. And so the equation that we want to use is the equation that converts kW to BTUH. And so if you've got BTUs per hour, that's a power unit, and so we can convert to kilowatts. If we had BTUs, we use the same equation, but it would be converting to kilowatt hours. So we're going to divide this by 3,413 BTUH per kW. Sorry, BTUH per kW. The BTUs are going to cancel out, giving us 126.6 kW. So that means for every hour that this unit is running, we've got 100, at this condition, we've got 126.6 kW of electric resistance going on. Now this is assuming that the electrical resistance is running at 100% efficiency, which it typically is unless there's coil degradation. So if you have a problem that doesn't list the efficiency on the electric resistance coil, you can assume that it's 100% efficient. So if we've got 126.6 kW and we're running that way for 8 hours, that means we have 1,012 kilowatt hours. Actually, it's 1,013 kilowatt hours for 8 hours. And so another thing that I want to make sure that everyone hears, because it's a common problem that I'm seeing on homework, is there'll be an equation like this and somebody will be off in their calculations. And so I'm going to erase this really quick. just so I have a little bit more room. And a lot of times what will happen is, let's say we figure out that it's 432,000 BTUs per hour, and we're trying to convert to kW. Sometimes I'll see someone say, okay, I think it's 3.413 BTU-H per kW. So we're off by a factor of 1,000. So let's do that equation really quick and divide it by 3.413. And so that equals 126,574 kW. And then we multiply that by 8 hours. And we come up with 101.2599. So 1,012,599 kilowatt hours. And they'll put this down as the answer. And what you need to start getting to the point at is starting to put things into context and start realizing the weight and the size of units that you're dealing with. So if you're using over 1 million kilowatt hours for 8 hours, you can start saying, okay, well, what if this unit is running for 4,000 hours a year? You know, now all of a sudden we're using 506,299,443. We're using 506 million kilowatt hours per year. And if nothing else, you can start applying the factors of saying, how much is a kilowatt hour, how much is a therm? A good place to start is to say that a kilowatt hour is 7.5 cents and a therm is 75 cents. That's not exactly always what it'll be, but you can at least start putting that kind of image in your head. And so if it was 7.5 cents per kilowatt hour, per year it would be 379,72458. It means to run one 10,000 CFM air handler, it would cost you $37 million. And I see this put onto homeworks, and I've seen this put onto the midterms, and this is the reality check that you need to start having for yourself to say, that doesn't make any sense. We've also seen it go the opposite way, where maybe you come up with a number that says it's going to cost $37.48 per year in electricity. And again, you have to use the logic in your head to say, okay, what does the electricity cost my house for the course of a year? You probably don't pay $37 a month. So how, when we come up with these equations that come up with $37 a year for a 50,000 square foot building, it just doesn't make sense. And so you really need to start thinking about the numbers you're putting down and really understanding if that makes sense, or if you have somehow been off by a factor of 1,000 one way or the other, or a factor of 100 one way or the other. But it's a good way to kind of check in and see if you're in the ballpark. If you come up and say this air handler is going to cost $37 million a year to run, or it's going to cost $37 a year to run, you're off by a multiplier, a big multiplier, and it needs to fall somewhere in the middle. So I encourage you to start putting dollars to your numbers to understand how far you are off.